In this video, I'm going to do two rather short but very interesting proofs that go back to the 19th century. The first of them will show that in a spherical triangle, the amount by which the sum of the three angles exceeds 180 degrees is numerically equal to the area of the triangle if you express everything in radians. And in its twin, the hyperbolic version, you will discover that the amount by which the sum of the three angles of the triangle falls short of 180 degrees is equal to its area. So let's start with the spherical one, because there the area is quite a bit easier to visualize. For convenience in drawing, I have chosen a triangle ABC for which vertices A and B are both on the 90th meridian of west longitude. That is, they're right at the edge of the region that we can see. And I place vertex C a little bit east of the prime meridian. This is going to make it very easy to do the proof, but I should point out that given any pair of vertices A and B, it would be possible to perform a rotation that would put them on this meridian. So in that sense, this is not a special case. Now let me define a loon. Remember common notion 9 of Euclidean geometry? Two lines cannot enclose a region or enclose an area. In spherical geometry, that's not true, and the area enclosed by two lines, that is, two great circles of spherical geometry, is a loon because it's kind of the shape you see of the moon when it's somewhere in between new moon and full moon. So let me identify the loons on this diagram. Here's my triangle, ABC. Here is a region that I have labeled RA. And let's combine those two regions into one and look at the boundary. One boundary is a great circle that goes from A to C and is then extended around so that it reaches the point that's antipodal to A. So this distance is half the circumference of the Earth. Similarly, we have another line of spherical geometry that is the meridian from A to B, extended down around the South Pole and back up through part of the southern hemisphere to the point antipodal to A. So this is a line of spherical geometry. This is a line of the spherical geometry, and the region that they enclose is a loon. Now let's combine TR and RB. You've probably caught on to the general idea by now. I extend the side of the triangle from B to C around till I reach the point that's antipodal to B. I consider the meridian going up from B through A around the North Pole and down to the point antipodal to B. And those two regions together form a loon where the opening angle is the angle between these two sides of the triangle, or equivalently, the angle over here at the antipodal point. Strictly speaking, region TR and region RC do not form a loon, but if I were to take RC and move it over and put it on the opposite hemisphere, joining on at AB, I can do that because this distance from A to B is equal to the distance between the two antipodal points. Then TR and RC would also form a loon, and the opening angle of that loon would be angle C. So our next task is to figure out the area of a loon. Well, if you think about the loon formed by two meridians, it becomes clear that the fraction of the Earth's surface occupied by such a loon is proportional to the opening angle of the loon. The portion of the Earth's surface that lies between the prime meridian and the 60th meridian east is twice the area that is in between the prime meridian and the 30th meridian east. And we know the total surface area of a sphere. It's 4 pi. 4 pi what's? Well, the usual term is steeradians, which is used in place of square radians. And therefore, I can say the total area is 4 pi. A loon with opening angle theta occupies a fraction of that area, which is the ratio of theta to 2 pi, and therefore the area of a loon with angle theta is numerically equal to twice the angle theta. I will be able to confirm that the use of 4 pi for the total surface area of a unit sphere is correct when I show you that in the case of a small triangle, the area as given by this approach agrees with its area in Euclidean geometry. So here I've taken my triangle ABC and I've actually labeled all the angles. This is a good big triangle, and you can see the three angles of the triangle sum to substantially more than 180 degrees. Now I'm going to have to flip back and forth between two diagrams for this argument. We saw that TR and RA together formed a loon. Here is that loon, and the angle of the loon is A. Similarly, TR and RB form a loon, and the opening angle of that loon is B, so its area is 2B. And finally, TR and RC, though they didn't actually form a loon, have the same area as a loon with opening angle C. So I'm not going to add these three equations together. On the left, I get TR plus RA plus TR plus RB plus TR plus RC. On the right, I have twice A plus B plus C. But if you look back at the diagram again, you can see that RA, RB, RC, and TR together form a hemisphere, and therefore the sum of their areas must be equal to 2 pi. I subtract that off. I get rid of RA, RB, and RC, but I have two TRs left over on the left-hand side, and on the right I have twice A plus B plus C minus 2 pi. Divide everything through by 2, and I've got my conclusion. The area of the triangle is A plus B plus C minus pi. If you're doing this course for graduate credit or for math concentration credit, this is one of the 8 proofs that you'll have a chance to present as the sort of math concentrator final exam. Now this is something I had never tried before, making a smallish right spherical triangle. It's smallish but not really small. I'm going to make its base be 120 nautical miles, which is equal to 138 statute miles. Why is it equal to a nautical mile? Because by definition, a nautical mile is the length of 1 minute of longitude at the equator, and there are 60 minutes of longitude per degree. For the height, I'm going to use half that amount. I'm going to go 1 degree up the prime meridian. That's 60 minutes or 69 statute miles. And if you calculate very carefully the angles in this triangle, you see that the two acute angles sum to ever so slightly more than a right angle. So you've got to have a triangle whose sides are in the 70 to 140 mile range before you can start seeing any significant increase of the sum of the three angles over 180 degrees. So the formula we just proved says that the area of this triangle is equal to the sum of the three angles minus pi. Everything has to be expressed in radians for this to work, and I get 0.0003 and change. Here I'm measuring distance in radians, so if I want to do Euclidean geometry, I also have to measure distance in radians. That's not hard. 2 degrees is about 0.035 radians. 1 degree is half of that. So I take 1/2 a times b. And when I multiply it out, this is a strictly Euclidean formula, I get agreement to 7 decimal places. The answer is in the 8th decimal place. So this shows that this triangle, though it's fairly large by geographical standards, this would make a very reasonable size island if it were one, it's still small enough that Euclidean geometry gives us a very good approximation to its area. And this is confirmation that I did the right thing in using 4 pi, a result that's usually derived using calculus, for the area of the entire sphere. Now let's do hyperbolic geometry. This proof is actually a little bit simpler, but the starting point is kind of weird. The hyperbolic plane has infinite area, but there's an upper limit to the possible area of a triangle. The largest possible triangle I can make is one where all three angles are 0 degrees. You say, that doesn't look like 0 degrees to me, but it is. These two sides don't actually meet. They're asymptotic to one another. They become parallel lines on the hyperboloid as we get very, very, very far away from the bottom point on the hyperboloid. This is a so-called triply asymptotic triangle. It has 3 0-degree angles. And furthermore, since in hyperbolic geometry the angles of a triangle completely determine the side lengths, any two triangles that satisfy equal angles are not merely similar, they're congruent. So that means all triply asymptotic triangles are congruent, and therefore they all have to have the same area. I'm going to decree this area to be pi, and my justification will be that when I work out the area of a small hyperbolic triangle, the area will agree with its Euclidean area. Now let's suppose I take this triply asymptotic triangle and decompose it into 3 smaller triangles by breaking it up at a point in the interior. These triangles are so-called doubly asymptotic triangles because each of them has 2 angles of 0 degrees and 1 angle which is not 0. It's clear that the sum of the angles alpha, beta, and gamma is 360 degrees, or 2 pi radians. If you think about what happens as alpha approaches pi, these two sides get closer and closer together till eventually they agree with this side and the area drops to 0. So if A is pi, one of these triangles has area 0. If, on the other hand, I make the angle alpha approach 0, this triangle turns into the full triply asymptotic triangle, and its area is pi. We know that the area of a triangle in hyperbolic geometry is going to depend on its angles, and therefore these 3 areas have to be pi minus alpha, the amount by which the sum of the angles falls short of pi minus beta, and pi minus gamma. And if I add those three areas up, I get pi plus pi plus pi minus alpha plus beta plus gamma. Alpha plus beta plus gamma is 2 pi, so I've got 3 pi minus 2 pi, or pi as required. Now let me put in an arbitrary triangle. So here's my triangle ABC shown in the Klein model. I will extend side AB till it hits the circle. Label that point V2. I will extend AC to V3. I will extend BC to V1. And I have constructed a triply asymptotic triangle whose area we know is pi. And now it's going to turn out to be a very simple matter to calculate the area of TR for the simple reason that these other three regions are all doubly asymptotic triangles. And we know that for a doubly asymptotic triangle, the area is pi minus the non-zero angle. So for this, it's going to be pi minus the quantity pi minus alpha, or alpha. So RA is a doubly asymptotic triangle whose area is alpha. RB has area beta. RC has area gamma. And the sum of these three areas is therefore alpha plus beta plus gamma. But if I add in the triangle, then the four regions, RA, RB, RC, and TR together form a triply asymptotic triangle. We know the area of that, it's pi. And since the three regions outside the triangle have combined area alpha plus beta plus gamma, we have proved the area of the triangle is pi minus the sum of the three angles. This theorem was discovered by Gauss, and he was sufficiently pleased with it. He actually hired teams of surveyors and set up transits on three mountain tops to try measuring the three angles. Unfortunately, within the error of measurement, the result came out consistent with 180 degrees. Now let's finish up by doing a smallish right hyperbolic triangle. You can think of this as laid out on the base of a hyperboloid. And a hyperboloid is flat on the bottom, just the same way a sphere is pretty flat on the top. And I'm going to use the same hyperbolic lengths. 2 degrees expressed in radians. So for the base, a hyperbolic length of 0.036 radians. And for the height, half that, 0.018. I can calculate all the angles in this triangle, and if you look at it very, very carefully, you have to go to 2 decimal places after the decimal point. You see the sum of the acute angles falls ever so slightly less than 90 degrees. That's what happens with hyperbolic triangles. So if I take pi minus the sum of the three angles, I again get 0.003 and change. If, on the other hand, I take 1/2 times the altitude times the base, measuring things in radians, this is the Euclidean formula for the area of a right triangle, I get 0.003241, and then we differ in the 8th digit after the decimal point. So the Euclidean calculation of area agrees very closely with the hyperbolic calculation. The reason it only agrees with it closely is that these two triangles actually do have slightly different areas. One is on the surface of a hyperboloid, while the other is in a true Euclidean plane. So there you have it. If you're doing the concentrator's final exam, you should learn these proofs, but they're really quite easy, and they're great fun to know because especially the spherical one is one that you can present to any attentive person if you have a globe at hand to illustrate what you're doing.